Okay. Okay, so welcome everybody to the webinar of today. That's the first webinar of the year 2023, and to open the year, the presenter of today, the speaker of today is Jean-Paul Bonnet. The title of his presentation is Experimental and Computational Fluid Dynamics, Decades of Turbulence, Turbulent EFD, CFD Complementarity. So as usual, I introduce the speaker very briefly, and then I leave him the floor. Jean-Paul Bonnet is currently a senior researcher director at CNRS and emeritus professor at the Laboratoire PEPRIM in Poitiers. He has over 30 years of experience in turbulent free and boundary shear flows, essentially from experimental approaches in wind tunnel. He addressed compressible high velocity flows, transonic and supersonic, subsonic flows, subsonic and flow control, passive and active flow control using pneumatic and plasma methods for noise abatement, separation, and drag reduction in turbulent boundary layers. He develops several approaches for data processing, such as multiple decomposition concept, linear stochastic and proper orthogonal decomposition, and low-order representation of turbulent flows. He develops both fundamental and applied items with about 10 patents, several industrial collaboration, international network. He published more than 400 articles, communications, reports, etc., and organized more than over 15 symposia, workshops, and courses. He supervised over 6 books and co-authored with Tom Gatsi, Compressibility, Turbulence, and High-Speed Flows. He is associate editor of International Journal of Heat and Fluid Flow, senior member of French Association 3AF, and corresponding member of French Air and Space Academy. So it's with great pleasure that I introduce Jean-Paul Bonnet for the seminar of today. So Jean-Paul, I stop sharing my screen, and you can start sharing yours.
Should I say yes? Yes.
Yes, you can start sharing your screen.
Is that okay?
It's yes, it's I see it. That's perfect. It's looks good.
Okay, so thank you very much, Francesco. Thank you for this lab, for inviting me. I am very happy to see here so many people that I know before, and such a beautiful installation for experiments and for CFD. So my talk, as Francesco said, is a view of experimental and computational fluid dynamics, and
just a second, I think we lost the audio. We don't hear you anymore. Yeah, no, now it's good. Now it's good. No, it's good now.
Yeah, but you cannot switch.
I cannot skip for the. I can stay here for half an hour, but maybe. Je comprends pas, je le sors simultanément. Échappe. Ça avance. Donc là, si je refais ça ici, et là, ça va avancer bien. Is it okay like this?
Yes, but you need to always remove the presenter option. So just remember that.
On a fait ici.
Yes. C'était là, masquer le mode de présentation. Ah, super.
Et là, yes, it works. Okay.
Right.
So, thank you. So my talk today is based on a special issue of compte rendu de mécanique, which is for Académie des Sciences in Poitiers, in Paris, because they issue special issue of the journal that is called More Than Half a Century of CFD. And during the discussion, by building this special issue, they want to ask somebody who is not entirely in CFD to see what is his view of this half a century. So I want to say just in advance that it's very important to say there is no scoops in this talk, there is no new results, there's just a personal view of this quasi-parallel evolution of experiments and computations. And this is an entirely non-objective, non-exhaustive set of illustration. I want to apologize in advance if somebody is not cited in this talk. So I will split my talk in several parts as usual. First, I will describe my view of the evolution of the perception of the physics of turbulent flows from random to organized behavior. Then I will try to see what is bring from experiment to CFD and the reverse. Discuss a bit on common tools that are shared between EFD and CFD. And flow control, I will spend some time on flow control because in my mind, this is an illustration of complementarity. And conclude. So during, oops, what, how can, hello Andrew. May I take this off? Okay.
Enlève ta souris du haut, ça va partir. Oui.
Okay.
Ça va.
I will try to do that. Maybe I can put this on the. No.
I will take care of whoever enters, no problem.
So during the 80s, so I'm back now to the 80s, this is the last century, for the longest. Experimental fluid dynamics was concentrated to one point measurement for giving mean and statistics. And for CFD, using the Reynolds or Favrian, if you are in compressible domain, and then obtaining the average Navier-Stokes equations that everybody of you knows about that. And initial data from the experiment were essentially used for giving the data were essentially used for initial data and for validations. I cannot, I'm not still be able to split.
Click on your application.
I will stop this.
No.
And then back. This one. No, sorry. What happens?
C'est bon. On voit.
We see
Pas passer. I cannot.
Essaye je crois, de cliquer sur l'application, parce que ça clique mieux. Tu cliques quelque part ici, et ensuite essayer de faire passer.
Là, ici, là, peut-être là. Mais là, moi, j'ai l'ensemble des.
Non, c'est pas bon. On remet sur l'autre mode.
Je reviens ici, masquer le mode présentateur.
Tu vas enlever ça.
Là, ça marche. Oui. Bon, ça fait rien.
Essaye de ne pas toucher là-haut. Et comme ça, si tu as sur la présentation, ça va aller.
Faut pas que je touche là-haut.
I think it's on the 3 dots. You can have mask.
Ah, où c'est ça?
Maybe there should be mask.
Masquer et comment on peut tourner
ça? Wow. Oh, okay. So, I know, but I am not.
Refais le truc ressortir et re-rentrer.
Faut que je ressorte et que je rentre.
Ouais.
J'arrête ici?
Ouais.
OK. Et là, je reviens à partager l'écran. Bon, partager. C'est toujours le truc là-haut. Mais bon, ça fait rien, je vais laisser le truc là-haut.
Oui.
Mais là, je ne peux pas passer, je ne peux pas changer. C'est incroyable.
Et en bas à gauche, on peut changer avec les flèches, oui.
Oui, voilà la petite flèche.
À gauche, oui.
Ok, good. Parfait.
Du coup, tu peux cacher là-haut maintenant, si tu veux.
So, save time now because starting during this 80s, there was essentially hot wire and a bit of laser Doppler velocimetry, but mainly 1 point, maybe 2 points if you have two hot wires. Spectra and giving essentially RMS value, indeed mean values, but also RMS and spectra. Spectra can be very important indeed for this topic. And CFD uses turbulence model for different kind of computers. And okay, I will stay here. So at that time, this was essentially comparison of experiments with CFD. And there was a special Stanford conference in the 80s that was called complex turbulent flows. At that time, there was 5 kilograms of CFD in the books that were distributed during this meeting. So essentially, the CFD were compared with experiments with this kind of thing, okay? With this kind of thing, comparing the average values, the fluctuation levels, and so on, and comparing different turbulence models. So from that time, things have evolved, and also people have evolved. Okay, so, but as you can see. And then at that time also, this was a question that were distributed among all the researchers, is that what is the future of wind tunnel testing? And many people were thinking about numerical wind tunnel test. That is, at that time during the 80s, many people were thinking that 20 years later, or maybe 30 years later, there will be no need for any experiment, but everything on numerical wind tunnels. It looks like this. Okay, so at that time, the turbulence was seen as an entirely random process, just coming with signals that have average value and RMS value. Then all the results from the experiment were compared with the computation on the mean values, mean velocities, or fluctuating velocities. But during the same time, at the end of the 80s or about the 80s, the observations of some experiments shows that there is some part of organized motion, even in turbulent flows. And the results of Bob Falco was very illustrative at that time. In boundary layer, he shows that what he called mushroom structure, longitudinal structure, sweet events, and so on, in boundary layer. So this comes to change the mind of many CFD people saying, there can be something organized in flow, so the RMS value is perhaps not the only thing that is important for turbulent flows. And we start thinking about order or chaos. And this was not very new because from Leonardo da Vinci, in his drawing, he shows that something is organized in these very chaotic flows. And you can see in several natural flows that there is some organized motion in the turbulence. And then at that time also the French school, to be clear, was very much engaged in this direction. And for example, the group of Pomo, Berger, etc., were issued a book that is still available, and it's called L'ordre dans le chaos, Order in Chaos. And other theoreticians prepare the description, the dual description of the turbulent flows. Indeed, order and chaos, even at that time, is not so obvious because you can have order and chaos in this kind of flow, for example, in a wave that is very close to you here, where you can very easily see on the spectra that there is a peak that's given structure in the flow. This is clear. But if you look, for example, in boundary layers, you can see that there is several structures in this flow, as Bob Falco showed, but the spectra do not exhibit any peak in average. So the question at that time is that, providing we know that we admit that there is some order in the chaos, how to separate order and chaos in this kind of flow? In this case, it can be very simple when you have a peak, but in this case, it's not at all the same problem. And then I enjoy this sentence of Keith Moffat, but because he wrote 10 years ago that coherent structures became a growth industry. I enjoy this term, growth industry, during the 70s and 80s, and with a return toward a mechanistic approach based on vortex interaction. It's very interesting, in parallel with the purely statistical approach. Then there were, after this time of the 80s, ending by kind of 20 years later, there were a rapid development, you cannot see here, but on the PIV, introducing, due to the progress in laser, in computers, and in cameras, the development of that is very well known now, PIV, with essentially work of Adrian and Michel Stanislas here, indeed, and in parallel, the development of large dissimulation, in which the structure are separated, or the distribution of the component of the turbulence are separated with part which can be modeled as small scales and larger scales that can be resolved. And then, okay, this was a large progress due to Paris Morin, Marcel Lesieur, our distinguished colleague Marcel Lesieur, Pierre Sagot, etc. At the same time, I should say that Ramin in Toulouse developed a semi-deterministic approach that is still in use, for example, in Toulouse. After that first stage, then there were an increase in the capabilities of the laser and cameras and computers. Then we saw now stereo PIV, time resolved PIV, and for the computational side, DNS indeed, and the unsteady range, Boltzmann approach, DS, and so on. So at that time, it was necessary to introduce formalism for this separation. And then, thanks to Fazli Hussein and Bill Reynolds, not Osborne was they introduced a triple decomposition in which the velocity is separated in one average, one statistically random, which is you hat, and you tilde, which is the covariant part. And this was a very important progress for the formalism of this approach. And at the same time, Fazli Hussein asked the question, coherent structure, reality and myth. This was a real question at that time, which is now no longer a question. But for that, you have to be able to determine what is, how we can measure or estimate from CFD this quantity here. And then the question that was shared between experiments and computation is how to characterize. And in this case, there is globally two kinds of approaches. One is non-conditional, the other is conditional. For non-conditional approaches to extract, that can be space-time correlation, spectral analysis, for example, for the case of the wave, this is very simple, but not in boundary layers, and the proportional decomposition. I will be back a few minutes later on this proportional decomposition, which is based on two-point correlation. Conditional methods are very, there is a lot of conditional methods. There is a fluctuation level. You can just decide that the flow is organized when there is a given energy. 4 quadrants, and these methods are still in use for experiments of CFD. 4 quadrant is based on the sign of the two components of the velocity fluctuations, for example, in boundary layers. variable integration, time space average, gradients of vorticity, Q value, lambda value. I will not give in details on that method because you can find this in the literature very easily. And then some methods which are in between. This is pattern recognition technique, linear stochastic estimation, wavelets, and now wave packet for the acoustic studies at that time. I enjoy I will skip this too, because just, okay, I can't stay there. I'll just give here the different ways that some of those methods are able to extract the flow. I will try to move this. I hope it will be secure. If you have this kind of flow structure, which is complex, this is a structure that has been determined by very detailed PID measurements, and then trying to use different techniques for extracting this structure, you can see that vorticity magnitude is not so good. Swirling strength is very good to extract this structure and the structure in the wake. The normalized angular momentum from the group neon is very efficient. And if you just look at the energy, turbulent kinetic energy, it doesn't work at all. So as I was expecting, it doesn't work there. And okay, I am lost, so I have to move on. Maybe. I try to do this again. And now it works. Now it doesn't work, so I want to stop this one. Okay, and be back to the, sorry for that. Partage. And here I have to, non.
Masquer, oui, masquer.
C'est bon là?
Tu peux masquer, plus masquer.
Oui, c'est bon, c'est bon.
Qu'est-ce qu'il faut que je fasse ici? Ça y est, je suis reperdu. Ah, ici? Non.
Ah, ça, c'est bon. Si tu veux vraiment t'en débarrasser, enlève-le.
Ah, ok. Partager? Non, j'y suis déjà.
Okay.
Et là, c'est bon. Ok. Alors, donc là, on est bon. So I present this view because I enjoy this picture. This was during at the end of 19 to 2000. There was a meeting in Udine in Italy where I am pleased to introduce people. This is my late colleague Joël Delville, but Olivier Mété, he was working with Marcel Le Sieur, working on this large AD simulation. Fazil Hussein, I described you a few minutes ago what is his input. John Leblay, that introduced the POD, and myself, Ron Adrian, introducing PIV and the lambda method, and Christos Vassilikos, who was using this waveless approach at that time, from that time it was. So now, after that, I can just go back now to the real and actual position of this experiment compared to the computation. So experiments indeed can provide the initial condition for any CFD and also turbulence level, scales, and spectra. I should insist on the fact that this is always difficult from experiment to provide good data on the turbulence incoming, for example, in a wind tunnel, because the levels are in general very low, and then so low that they can be higher than the noise of the measurement technique. So it's very delicate measurement, very important for several computation. Experiments will give mean field stresses for turbulence model, indeed, organized structure, I said that before, and turbulence scales. Also, some delicate measurement are the measurement of transition, because it's a delicate measurement due to, let's say, perturbation in wind tunnel, etc., etc. Experiment provide control concept. I will be back on that point later on. They can also give information of noise, but noise is difficult because you have the noise sources, the propagation, and measurement of a quantity which is not local, like the pressure, is always difficult. And the compressible flows that are of great interest for industrial application, for example, then they are difficult to measure because of presence of shock, etc. However, what is very important of experiment to computation is a long temporal series, is the evidence of rare events that we were discussing on that a few minutes before here. There is still some limitation in this experiment towards the computation, is a wall proximity, 3D effect. Another point which is not so obvious is to combine simultaneous data of different nature. For example, if you have PIV data, if they are not resolved in time, they are sampling at a given frequency. And at the same time, if you measure the pressure is a continuous signal, or temperature, and so on. So you have to deal with data that are simultaneously measured or not simultaneously measured. Uncertainties at that time with the PIV data storage is a big challenge, and time resolution for PIV, particularly in high-speed flows. Just one example that we develop in Poitiers for, let's say, helping the experiments, the CFD from the experiments was the generation of initial conditions for large eddy simulations. In this case, for example, we start in a mixing layer with a plane which is span-wise in the Y and Z direction to obtain this snapshot POD. But at that time, the snapshot POD is not resolved in time, and then or in space, we adapt the POD to the meshing of the CFD, in this case, which is a large eddy simulation, and then we can put some time evolution just by putting some random signals. And we were able to generate a very realistic initial conditions for LAM. And as far as CFD, I should put this off. Another time I will try. Okay. At this time, computation can provide, and this is relative news, all the wind tunnel test condition design. I will give you an example on that, what I mean by that later on. For parametric studies, I will give you also an example of the optimization of flow control. CFD can be absolutely essential. Data assimilation, indeed, is possible from CFD to complement the missing data from experiments. Another point also, which is specific to computation, is to be able to determine with great precision some data, like skin friction, for example. Drag reduction is not so easy to measure experimentally, and you can obtain this indeed from CFD. Some energetic balances, heat transfer, etc. CFD is also able to introduce complex physics, like multi-phase, thermodynamics, etc. Again. Bon, il faut que je revienne là-dessus. Et si je fais ça, je reviens là-dessus ou pas? Non, bon. Bon, je vais arrêter dans le truc là-haut. Alors, à nouveau, partager. À nouveau, partager. OK. Non. Ah oui, là, il faut que je... Ah, j'ai à nouveau plus la main.
C'est bon, plus là. Merci.
Ah, c'est bon là. Like in the experiment, transition is still a delicate simulation topic. Noise is also delicate for the same reason, for the sources and propagation, and compressible flows because there is shocks, and high speed, different species in shock. Then the other point is that this is able to give to the experiments the entire flow field variables. mainly for DNS and LS. He did less for runs and 3D descriptions. There is still limitation, like the prescription of initial condition, the wall proximity for some techniques, for some approaches, meshing requirements and data storage, about the same as for experiments, and often limited time duration of some computations. So what I wanted to say about the definition of wind tunnels, this is an example of the large wind tunnel of Onera, which is in modern Avrieux, which is the biggest in Europe. It's the biggest in Europe. When you have to design an experiment with a model like this, you have to hold the model. So you have to know all the perturbation of the flow all around due to holder of this model, what are the forces that are present on the holder to design it in the best way, etc. In this case, the CFD, even low, let's say, capability, not DNS indeed, but with a low order model, you are able to determine the best way to handle this model in the wind tunnel and to take into account the perturbation in all the wind tunnel. You can find many examples of that in a book which appears 2 years ago, Experimental Aerodynamics, an introductory guide, and which I mentioned to Jean Beneric, who passed away some weeks ago. So there is another input of CFD to experiments is the question of Reynolds number effect, because in wind tunnel, academic wind tunnel, we have Reynolds number which is about 2 orders of magnitude lower than in airplanes. This is about 10 times 1 order of magnitude for national organisms like Onera, DLR. But at that time, there is specific effect of Reynolds number. And after the DNS of Lee and Moser, we can see that, in fact, depending on the Reynolds number, the distribution of the fluctuations, for example, in this case of the longitudinal velocity, u prime squared, is different according to the Reynolds number. You can see that they have a Reynolds number that is varying in a proportion of 60 times, 70 times higher. And then you can see that the distribution of the fluctuation is very different. And then, for example, if you want to compute and to control this kind of flow, this can be very different if the repartition of the energy is like this or is like this with much more energy in the outer part of the mixing layer. There is also some data which are comparable in this wind tunnel because you are able to address a large variation of Reynolds number. And this is still a question for flow control of some techniques of flow control. There is some, okay, I said this before that the data storage, uncertainties, etc. We don't say that before, as before, but there is some opening, let's say, common studies like hybridation, data assimilation, all the data processing, and the machine learning and data-driven method that are shared by the two communities at that time, by experiments or computational fluid dynamics. This results that come from this laboratory shows how not only the experiments can provide data for the CFD, but CFD can be used to validate the experimental data. This was not possible to imagine this 40 years ago. And there, in this case, for example, they compare the DNS, which is without any model or any assumption, with the result obtained by autoanemometry in this case, going up to, let's say, 2 or 3 times the viscous units for this longitudinal component and higher for the other component compared to the PIV, depending on the plane of the PIV. So in this is a bit so the reverse of some years before. That is, DNS is able to validate the experiments. And there is indeed, you know, that some hybridation. This is using PIV in DNS computations that can allow to have much more detail in the description of the flow, and particularly important for this kind of thing, to provide, for example, the pressure field. And in this case, the pressure field is very realistic because of the hybrid experimental and DNS approach. I think that time is flying, so I will just give a few words on POD because I think that everybody, or mostly everybody, knows what is a POD. So just to remind you that from this description of the flow based on a two-point spatial correlation, we can obtain the eigenfunction and the orthonormal coefficient A's. And I'll just show you here a recent study that was that is developed in the US by Mark Glauser and Natalie Tonde. They start with a very applied problem, which is the problem of rectangular jet. You can see what kind of use of rectangular jet they have in mind, but they simplify the flow by addressing a flow which is a wall jet flow into a bulk jet. So this is, as you can see here, this is a main jet, and there is a wall jet flow coming at the exit of this data. So they perform, let's say, experiments like Schlieren visualization, that is density visualization, and they run a large AD simulation, which is very good, in very good agreement with the experiments. Okay, at that time, there is nothing new. But what happened is that they tried to look at the spectra of the proper orthogonal decomposition coefficient. The POD have times some coefficient that depends on the eigenfunctions that you are looking, the structures that you are looking. And if we look here at the first 2 or 3 first mode of the POD, they observe that from their Schlieren sampling at 50 kilohertz, that there is a peak here. And this peak at about 16 kilohertz is not physically easy to understand. Yeah, skip the details, but they were astonished with this one. So they decide to do the following. They decide to use, as they say, a fusion between computational experiments. This is a bit the same thing that I present you for the initial data for LAS before. Providing here, the LAS data can resolve the A's because it's LAS are very well resolved in time. But the convergence for the LAS is very poor, and the eigenfunctions here are not very reliable if they come from LAS. But for experiments, it's very easy to have a lot of data, a lot of samples, and have very good convergence. So they decide to use the A's for the LES and the phi from the experiment to observe the fluctuation of the density. If they do not make this hypothesis, they obtain this strange peak. And then in this case, the spectra here is 200 kilohertz, far higher. They can see peaks that are expected from the physics, but they no longer see this extraneous peak. So they call this the fusion of the data, but using these experiments, which are well resolved in space, but not resolved in time, and with LAS, which is better resolved in time, at least for this POD coefficient. For flow control, I propose to discuss a bit about flow control because this is a very pluridisciplinary approach, and many of you knows about this flow control that can be biomimetism, using vortex generators, using MEMS, using plasma. But all these kind of experiments are not so easy to compute because, because of the 3D aspect, the very low dimension, or some very complex flow configuration. However, from experiments, there is limitation in flow control. Flow control is an open area, still open area. But for example, if you want to adjust the placement of actuators of a sensor, it's difficult because you have to make a model, to change the model, to intervene in the model to change the location of the actuator and so on. Sometimes you are limited in terms of frequency range or spatial distribution and so on. So there is limitation for experiments. If we look at the flow control view from CFD, this is another story because you can imagine some very original ways to control the flow. I just give here two examples. One, which is a historical example coming from Choi and Kim, where they start with a CFD, where they can compute the streamwise vortex at close to the wall, and you can decide to adjust blowing and suction in order to cancel the effect of this longitudinal streamwise vortex. And then this is very good for the efficiency of that, but you can see that for an experimental point of view, it's very difficult because you have to know where is this streamwise vortex, and in turbulent flow it can happen everywhere close to the wall, and you have to decide where you blow or where you suck. So it's nearly impossible from experiments. Another way to try to reduce skin friction is to have span-wise actuation. From a CFD, DNS, for example, Quadrio obtained very good results by using to 40%, about 50% of drag reduction, of skin friction reduction. But to realize this kind of wall actuation, it is very difficult. I just say that in Choi, in UK, or Nicolas Bénard in Poitiers, with plasmas they can play with this 3D. So this is a view here, for it from the back here. There is also some other ways to obtain this from experiments, but it is very difficult. This is a Kagome lattice in Imperial College or others. So there is a bonus for optimization for CFD because you can very easily change the actuator placement. You can easily decide any sensing anywhere in the flow. And you can change the frequency range of your excitation, for example. But there is still limitation because if the geometry are too complex, if the geometry is evolving, for example, you have to remesh. If the flow is compressible because you can have the presence of shocks, etc. I will skip this example just to save time to give you one example of what is possible only if we associate experiments and CFD. And this is the case of the riblets. I think maybe some of you know this technique to reduce the skin friction drag by mimic this shark skin using this kind of longitudinal riblets. From the experiments in 2000 about, there were experiments that were developed, especially in Bonnet, but also in Poitiers, but anyway, they were able to see an optimum of reduction of skin friction, but with a large, let's say, uncertainty in the measurement, because measurements are very delicate for CX and CX in this case. And they decide to see, is it possible to imagine new configuration? You should know that the size of this protuberances here is order of micrometers. So it's very difficult to machine. So they start with the idea of what happens if we have this 3D configuration of the riblets. Instead of having a longitudinal one, we can have some S-shaped riblets like this. And then they indeed make here DNS. And what they observe the total drag is higher than the natural one. This is the drag here, and this is the distance from the beginning of the actuation, uncontrolled flow, and you can see that the total drag is higher. And the question is why it is higher. from an experimental point of view, you cannot say why. But from CFD, you can observe that there is two components of the drag itself: the friction drag, which is a real longitudinal friction drag, and the pressure drag. Because as far as you have some slanted of these protuberances, there is a pressure drop, a pressure drag due to the inclination of this actuation. And so this is not possible from experiment. So fortunately, you don't have to spend money to define a new description of rivulets. An ultimate use of experiment and CFD is developed in Toulouse with a group of Mariana Braza, in which she has a ring here with actuators on the shape, with actuator on the trailing edge, high frequency here, low frequency here, and without the CFD, which is behind this, it is quasi impossible to understand the physics, and maybe you need to improve this. So in conclusion, I will say I can skip this now. Okay. That EFD and CFD during the 40 years evolved in a quasi-simultaneous and parallel way, from description entirely random to a mixed and a dual description with organized flows, organized events, and background turbulence, which is, let's say, random. Experimental and computational methods follow drastic evolution during these 40 years due to and promoting the evolution of cameras, lasers, and computer and softwares. Flow control is an illustration in showing that both approaches are required for innovation and optimization. Each method have still their limitation, EFD and also CFD, even the computer growing in capabilities. And the community should continue and improve the mutual fertilization. Sometimes, in some part, we can see that people from CFD have not the same language than people from experiment, and vice versa. And this is very important to have this mutual fertilization. And now the last question is maybe the input of, let's say, artificial intelligence, particularly machine learning, that can benefit for optimizing EFD or for CFD. For example, at that time, there is a lot of job made in developing a turbulence model, for example, using artificial intelligence. So they can benefit to both, let's say, domains, but I should say with my, let's say, large view of that it is important to never forget the physics of turbulence, even if you are very good in artificial intelligence, machine learning, etc. You have still to come back to the very real physics and let's say the turbulence cascades, the dynamical behavior of the different structure in the flow, etc., etc. So, okay, thank you very much. I will skip the last for your attention, and Happy New Year to everyone.
Thank you very much, Jean-Paul, for the presentation. I would suggest then to open the stage for question, and whoever would like to ask a question in the room, then just feel free to ask, or people in the virtual audience, just feel free to unmute your mic and ask a question. So is there someone in the room who would like to ask? Just
don't see any hands.
Okay, so then I can just check for the audience. So for the virtual audience, just once again, just feel free to unmute your mic, or you can write in the report.
Maybe you can start with one question, actually, Francesco.
Yes, go ahead.
You show some example of coupling between the DNS and experiments, but it's always, let's say, for a given physics for a given purpose, how do you see how it could be, we could merge DNS and experiments, let's say more regularly, and for that it can become a normal way of studying a flow, actually. Because it's always difficult on all the examples you show. I mean, it was designed very precisely. But do you think that machine learning, for example, or intelligence artificial will help to, in the future, to really take the benefit of both, actually, to...
I think that it can be a good way to take benefit of the limitation of each of these approaches. DNS, for example, you will be limited in terms of Reynolds number at that time, in terms of duration of the sign of the results, and also to the way to store these results. And I think that taking this in mind and the other way from experiment where this experiment are in the real world, if I can say, and then I think that probably machine learning that can extract information from the flow taken as an entire flow, from CFD, DNS, you have the entire field, for example. And for LES, for experiments, you will be limited. I think that artificial machine learning can extract the information you need from the one or the other approach. I think that can, I can say, this will not improve the Reynolds possibilities of the DNS. I don't think so. But the example of having these A's that are very well resolved in time, but for maybe short times, then you put this in the experiments, you can extrapolate to maybe a higher Reynolds number, or find some laws of Reynolds number dependence, for example, I don't know. But I think that with the machine learning technique method, you need to have samples of the flow. You need to have information and then to collect all this information all together. I think that the machine learning can take, when we use this data, take in mind, if I can say, take in charge the limitation of one of the other ways. I don't know.
Jean-Paul,
yes,
you described the time from 1980 to 2020, more or less, the 40 years from 1980 to 2020. You describe in terms of CFD and PIV. Do you see that period of government research as very different from the previous 40 years, 1940 to 1980? And do you see it as independent from it? So you concentrated on the period 1980 to 2020.
Yes.
Years. Before that, there was another period.
Before that,
1940, 1980. And listening to your talk, one may have thought that there was no need for 1940, 1980. The period 1980-2020 does not need the past.
this is interesting because I think that indeed this is a good point, because if we look before that period, what we have as very large was the approach of Count-Bellow and Costin, and this was not dealing with statistics, with organized motion, but going back to the real physics of the flow. And I think that during this time, I don't want to say that this has been forgotten, but not put as an essential point for progressing the idea of the turbulence. I agree. This was, and during the 40 years before that, there was no computers, and people were just concentrated to the hot wire and the pencil. And this was a very fruitful time because they introduced at that time the spectral description of turbulence. They introduced the energy cascades and introduced so many concepts, and that after that were supposed to be admitted or less understood. I agree. This was a tremendous evolution, but I was not born at that time. So.
Can I make a comment?
Please go
ahead.
I would like, if you allow me, to come back to the very last sentence of your very last slide.
Yes, please. You want me? Okay, I will try. Partager. Yes.
Okay, which was a bit related to the question of Christos. I think if we want to make progress, we have to understand first, and then by understanding, it's usually possible to build models. And we should not lose that as an objective, because it's true that accumulating data and running CFD programs is quite exciting. But what do we do with this data? And I think that today, any experiment should be run with a numerical simulation in parallel, and a numerical simulation of the type of DNS or LES, because our experience is that the running of both on exactly the same flow in parallel can bring a lot of understanding of what is going on. And I would like to emphasize this point.
Thank you, Michel. I entirely agree with you. That was my main message.
Is there some other questions in the room? Thank you.
I actually have one which is connected with this last statement that I think I understood, because it was a bit quiet from here. It's something with the future of our discipline, you know. We're talking about running experiments and numerical simulations simultaneously, but this tendency to produce data, is this tenable in the future? I mean, do we really need all of this data when birds can fly just with a couple of neurons and using their control system? Are we going in the right direction here or not?
That's a good question. I don't know. Really, I think that if we are running this at the same time DNS, or for example, because it's more powerful, or LES and experiments, you have probably to have in mind some scientific objective, not just to compare. You have to have in mind some scientific objective. When you see that, for example, maybe you can have as an objective to see what is the unsteady lift system. And then, if you have this in objective, then you can try to have both approaches. So I think you have to, it's better if you can have an idea of the scientific problem that you are addressing, in general simplifying this if you want to use DNS, because anyway, with immersive boundary methods, you can address complex flows. But for example, I can give you, if I can, no, oh, yeah, I have to share. I have another example. I had another example. Ça marche pas. Comment je peux remonter là niveau? Qu'est-ce qu'il faut que je fasse? J'ai oublié. Là, ça fait rien en bas. Non. Donc, arrêter. Qu'est-ce que je fais? Je reviens avec l'écran partagé. Partage.
En bas, c'est bon, tu peux ouvrir. En bas. En bas à gauche. C'est parti.
Qu'est-ce que je peux faire? Ah, ok. I had another example, which was this one. We had in Poitiers an actuator which is mimicking the physical chevrons to reduce the noise. And it was very difficult from an experiment to make all these experiments in detail around these microjets coming that way and this way, because the microjets are 1 millimeter in diameter and so on. But they are acting to modify the noise sources. And what we do with the group of Eric Lamballet, we just make a DNS of a part of this flow. It is not always necessary to mimic all the flow. If you have some problem in mind, you can reduce your need in terms of DNS, for example. And then we make this DNS with just two microjets like this, converging in a shear layer. And there we were able to better understand where are the physics, etc. So when we have something in mind, you can more easily probably make a computation and then compare and help your understanding with in this case with the computation.
I just have a question that really a follow-up Marcello's question. How do you see the interaction between CFD and the experiments? How can they profit from the strength and of each other, in the sense like in numerics, for example, you can switch off and on certain effects which you cannot do it in experiments, and in experiments you can keep the whole complexity of the system. So this can give you somehow an indication of the robustness of the prediction done by the numerics or in comparison with the numerics. How do you see other avenues of exploiting the strength of these two methodologies for proceeding in parallel?
At that time, there is there will be a special issue, for example, in heat and fluid flows, where we collect let's say, artificial intelligence or machine learning and so on, approaches to model the turbulence for, let's say, RANS or URANS studies. So at that time, experiments are needed and can be put as an ingredient for optimizing the models. I think I'll try to give you most example I have in mind.
I see. Potentially, would it be interesting also to do the opposite? So reinterpreting the experiments based eventually on run simulations, such that kind of it's a way to identify what an average approach cannot capture.
Well, yes, indeed. Yes, we can easily imagine that there is missing data in many experiments. So, for example, even for PIV, which are with very large fields, for example, you can miss some part of the flow because you are limited in the spatial resolution. And then you can easily imagine that CFD can provide you a detail, for example, separation at a corner. I just give this like an example. But if you are in a large wind tunnel, for example, in Onera or even in Orléans, Poitiers, even here, if you have let's say, a field of view which is, let's say, 1 meter by 1 meter, you cannot solve the very small details of what we call 3D distribution, let's say, around let's say, vortex generator, for example. Then you can probably make use of CFD to see what happens in detail at that level and see if the outer field that you can measure is in agreement with this kind of, let's say, local event. That's an interesting point of view. Yes, yes.
Okay, thank you. So let's see if are there other questions in the room? I
don't see it so.
I have one question to Jean-Paul.
Go ahead, please.
Jean-Paul, do you know an example of active flow control which has gone to real everyday application?
This is a very good question. At that time, there is a for automotive industry, I think that Peugeot now not the same. They have demonstrators with cars with vortex generators on the rear part. Do you have something in mind?
Remember when we were in New York, it's 2017, Jean-Paul,
Yes.
and Vignansky was there. And he had actually applied a flow control method for the
Yes, the tail.
the tail of the
At that time, yes, maybe the more advanced, it was from Luigi Vignansky, when he has on the, let's say, tail of the airplane. So you know that for the tail of the airplane can be used in case of a defect of one motor. So you have to give some extra lateral lift to compensate the motor. So you have to reduce the size of the tail. And then Luigi Vignansky has real demonstrator of that. But this is not put on a Boeing or on Airbus at that time. Yeah, clearly. No, that's unless we are developing research on flow control for 20 years now, I think we are still waiting for real application. I'm sorry to say that, but this is the case. So if you have any idea, just let me know.
There are quite a few applications of passive.
Of passive.
Passive, there are some examples, but my question was about active. So with jet of moving parts, has it reached the state of practical application on some?
No, for active, the active, the control of Luigi Vignansky is active because it's a flapping jet.
No.
But this is not on news. You know, the application can be. Okay, we're dealing with another subject, but I show you the applications that we had to reduce the noise by these fluidic chevrons. When we want to use this kind of application to real industrial items, then we end up on the point that there is a balance between the energy you put in your system to control it and the result itself. And for example, in our case, you need so extra pressure to drive the flow. Then you need tubing. You need to have the safety of this tubing because they are high pressure, they are added mass, etc. And at the end, the industrial says, okay, the ratio benefit and loss is not in favor of this actuation. And then they disregard that actuation. But to say that this is very, when we are going to industrial applications, there is not scientific aspect that appears. This is probably why some of those techniques are not used at that time.
Yeah, actually, also in the chat, they are mentioning a few applications for private airplanes and some part of deformable cars, like deformable surfaces on GT cars and Bugatti models. That sounds like the kind of field where active flow control is actually applied, that's somehow more for a luxury application rather than for civil engineering, like civil airplanes or large scale cars. Yeah. Okay. Okay. If there is someone else who would like to ask a question from the virtual audience, just feel free once again to unmute your mic or to write a question in the chat. Okay. So this does to be the case. Is there someone else in the room who would like to ask a question? Doesn't seem to be the case. Then well, we can. I think we can conclude the seminar here. Thank you very much, Jean-Paul, for the speech for the talk of today. And I invite the audience to thank our speaker once again. And thank you very much for having accepted the invitation and for opening the webinars of 2023.
Okay.
Thank you again, and hope to see you soon. To see you all next week. Good evening.
Okay. Thank you. Thanks.
Bye.